I know chemistry class flashbacks, but trust me, this is about discovering how these things pop up in your everyday life in surprising ways.
What we're going to uncover is that chemistry isn't just something you learn in a classroom.
Mm.
It's the secret language of the world around us.
Exactly. And speaking of the world around us, this chapter kicks off with a scenario I bet you've experienced firsthand. That uncomfortable feeling after you've eaten a bit too much. A little too much spice, one too many helpings. We've all been there. Now imagine rummaging through your kitchen for a quick fix. What would you reach for? Lemon juice, vinegar, or maybe baking soda? Think about what your gut is telling you here. If you're leaning towards baking soda, you're already tapping into some basic chemistry knowledge. See, that slightly bitter taste is a hint that it's alkaline, which means it can neutralize the acids doing a number on your stomach. It's like a chemical tug of war. And baking soda comes to the rescue.
It all comes down to this balancing act. Acids and bases counteracting each other. It's happening all the time, even in our bodies.
Mm, That's wild. But let's go back to those other potential remedies for a second. Lemon juice and vinegar. That sour taste, and sometimes love, that's a classic giveaway of an acid. We've learned to identify these tastes instinctively.
Our senses are incredibly powerful tools for understanding chemistry.
Hmm.
Just like you instinctively knew that sourness usually signals acidity, our bodies have evolved to detect these chemical signals in our environment.
It's like we have a built-in chemistry kit. And it's not just our taste buds that are picking up on these cues. Think about turmeric. Ever gotten a turmeric stain on a white shirt? That reddish-brown stain when you scrub it with soap is turmeric acting as an indicator,
Yeah.
changing color in the presence of the base in the soap. And then, boom, back to yellow with a good wash. Chemistry in action.
That color-changing magic is actually a fundamental concept we use in chemistry all the time. We call them indicators, and they help us visualize what's happening at a molecular level, even if we can't see the molecules themselves.
So we've got these indicators, like turmeric, that give us visual cues about acids and bases. But get this, some indicators even change their smell. It's like chemistry for your nose. Ever noticed how vanilla seems to lose its sweetness around something acidic like lemon juice? That's an olfactory indicator doing its thing.
It just goes to show that chemistry is a multisensory experience. We often focus on the visual aspects, but our sense of smell can be just as informative.
Okay, ready for a little experiment? Don't worry, we're not going full-on mad scientist here. Picture yourself with some common household items. Lemon juice, vinegar, baking soda, and those strips of red and blue litmus paper you might remember from school. You dip that red litmus paper into the lemon juice, and voila, it turns blue. Your taste buds already told you it was acidic. But now you have visual confirmation.
Those litmus papers, they're like our little pH detectives. They change color based on whether a solution is acidic or alkaline, giving us a concrete way to measure something we can't see.
And speaking of measuring, that brings us to the pH scale, something you've probably heard of, but might not fully grasp. Imagine a scale from 0 to 14. The lower you go, the more acidic things get. The higher you go, the more alkaline or basic. And right in the middle, at 7, you've got neutral substances like pure water.
It's a measure of the concentration of hydrogen ions in a solution. The more hydrogen ions, the more acidic it is.
So this pH scale is like a sliding scale of acidic strength, from battery acid at a super low pH to drain cleaner at the high end of the scale.
And everything in between. The textbook encourages us to think about testing everyday substances, like your morning orange juice, with a universal indicator which would show us its pH level. You'd be amazed by how acidic some of the things we eat and drink actually are.
Okay, so pH is everywhere, in our food, in our bodies, and even in the environment. But why should we care about it?
Well, for starters, our bodies need a very specific pH balance to function properly. Our blood, for instance, has a slightly alkaline pH of around 7.4. Even a small shift away from that can have serious consequences for our health.
It's like our bodies are walking a pH tightrope. And speaking of balance, I'm curious about salts. We know they're formed from acids and bases, but where do they fit into this whole pH spectrum? And what makes them so special anyway?
That's a great question. Let's talk about salt. And I don't just mean the kind you sprinkle on your popcorn.
Okay, yeah, there's got to be more to it than that.
It's easy to take salt for granted,
Hmm.
but it's a fascinating compound with a rich history. It's one of the most abundant minerals on Earth
Yeah.
and plays a vital role in many biological processes. And as you mentioned, it's also the product of a neutralization reaction between an acid and a base.
Okay, back up a sec. Neutralization reaction. What exactly is going on there?
Imagine a seesaw. On one side, you have the acid, and on the other, the base. When they react, they essentially neutralize each other's properties, like balancing the seesaw perfectly in the middle. What you're left with is salt, which is neither acidic nor basic, but perfectly neutral on the pH scale.
So it's like they cancel each other out, and what remains is this perfectly balanced substance. Salt, that's super interesting, but neutral doesn't have to mean boring, right? The chapter also mentions that common salt is a key player in various industries.
Absolutely. Take electrolysis, for instance. This process uses electricity to break down common salt into its components: sodium hydroxide, chlorine gas, and hydrogen gas. Figure 2.8 in the textbook does a great job of illustrating this process.
Okay, I'm looking at figure 2.8 now. It's like they're putting salt water through this elaborate maze, and out pop these incredibly useful products. What's the deal with sodium hydroxide? What's it used for?
Sodium hydroxide is a powerful base with a wide range of industrial uses. We're talking everything from soap making to drain cleaning
Hmm?
to the production of biodiesel fuel. And then there's chlorine gas. While potentially dangerous in its pure form, chlorine is a crucial component in water treatment, ensuring we have access to clean and safe drinking water. It's also used in the production of various plastics and chemicals.
Speaking of useful byproducts, the chapter mentions bleaching powder. I'm picturing something like a cleaning product. Am I on the right track?
You are. Bleaching powder is made by reacting chlorine gas with something called slaked lime. It's likely something you use indirectly quite often, as it helps make your white clothes even whiter in laundry detergent. It's also used in paper manufacturing and water purification, all thanks to that simple reaction with chlorine pass.
And let's not forget about baking soda, the MVP of my pantry. I use it for everything. But I had no idea it was also connected to this whole common salt electrolysis process.
Baking soda, or sodium bicarbonate as it's known chemically, is another incredibly versatile product we can derive from common salt. Remember how we talked about baking soda neutralizing stomach acid? Well, that's because it's a mild base. And when it reacts with the acid, it releases carbon dioxide gas. That's the fizzing you hear.
So it's the same fizz that makes pakoras crispy. It all comes back to chemistry.
It really does. Now, are you ready to dive into another fascinating concept related to salt? Let's talk about water of crystallization.
Okay, this sounds intriguing. Is this like water hidden inside crystals?
Exactly. Some salts don't like to travel alone. They hold on to water molecules within their crystal structure. The textbook uses the example of copper sulfate crystals. These vibrant blue crystals, when heated, transform into a white powder. And you can actually see water droplets forming inside the test tube. That's the water of crystallization being released.
Wait, so the crystals are literally holding on to water molecules? That's wild. What happens if you add water back to the white powder?
It's like magic. The powder reverts back to its blue crystal form, reabsorbing the water it had lost. The chapter also mentions plaster of Paris, which is made by heating gypsum, another substance that contains water of crystallization.
Plaster of Paris, that's what they use for casts for broken bones, right? It sounds like this water crystallization is hiding everywhere. What makes it so special?
It's not that the water itself is special, but its presence within these substances that gives them their unique properties. In the case of plaster of Paris, when you mix the powder with water, it forms a paste. This paste then hardens as it reabsorbs the water of crystallization, creating a solid cast, perfect for mending bones. So it's not magic, but pretty darn close, right?
That's incredible. It's like chemistry is full of these hidden mechanisms that we never even think about. It's mind-blowing.
It really is. And the best part is we've only just scratched the surface.
I'm ready to keep digging. But before we do, I think it's important to step back and consider why this all matters. I mean, we've covered a lot of ground here. Acids, bases, salts, indicators, pH, electrolysis, and even water of crystallization. It's a lot to take in. Why should we care about all this chemistry stuff? How does it relate to our lives beyond the textbook?
You're right. It's easy to get lost in the details. But the beauty of all this chemistry knowledge is that it's not just theoretical. It's the foundation of how our world works.
It's like we've been speaking the secret language of the universe without even realizing it.
Exactly. Acids, bases, and salts aren't just confined to textbooks and labs. They're in the food we eat, the water we drink, the air we breathe, even our own bodies. And understanding these basic building blocks unlocks a deeper understanding of ourselves and our world.
So it's not just about memorizing the pH scale.
Not at all. It's about recognizing the connections, the cause and effect, like how that squeeze of lemon juice can settle an upset stomach. That's chemistry in action. Or how baking soda can make a cake rise. Chemistry again.
It's like having a whole new lens to view the world through.
And it's not just about these everyday examples. Understanding these principles is crucial for tackling some of the biggest challenges we face. developing new medicines, creating sustainable technologies, even mitigating the effects of climate change. It all comes back to chemistry.
Wow, that puts things into perspective. This seemingly simple chapter has really opened my eyes to just how impactful chemistry is.
It's about asking questions, being curious, and never losing that sense of wonder. That's what I hope you take away from this deep dive. A newfound appreciation for the intricate and interconnected nature of our world, all thanks to the wonders of chemistry.
I definitely feel that. This has been an incredible deep dive. It's amazing how much we can learn from a single chapter when we take the time to really explore it. But before we wrap up, I have one final thought-provoking question for you. What if we could analyze the pH levels of historical events? Imagine the secrets we could uncover by studying the chemical traces left behind.
Now that's an intriguing thought. Could we analyze the salt used in Gandhi's Dandi March? Or perhaps even the mortar used to build ancient structures? It speaks to the power of scientific inquiry and the endless possibilities that unfold when we combine knowledge from different fields.
It's like chemistry is the key to unlocking the mysteries of the past, present, and future. Who knows what other hidden wonders are waiting to be discovered as we continue to learn and explore. Until next time, everyone.